Okay, so for the next three solutions, I'll do them with the mechanism provided, and I'll just talk my way through them. So ketone in our starter material, really the only thing that's going to be photochemically excited. So as normal, we have our one electron moving onto the oxygen, one electron moving onto the carbon. This gives us our diradical. Notice in this case there's really no easily abstractable hydrogens, so that encourages the likelihood of cleavage. So we're going to get a cleavage reaction at this position, so we're reforming our CO double bond but breaking this bond, and that would then give us this diradical intermediate where we've got cleavage and we've done ring opening. So when we look at this diradical intermediate and this first product, you'll see that we have our aldehyde. We can get to an aldehyde by hydrogen abstraction. The question is which hydrogen is going to get abstracted. That's controlled again by a way that not only is it conveniently located in space, but then it can also, by abstraction of this hydrogen, can lead to the formation of our double bond. So two good reasons why this hydrogen is abstracted, getting us to our aldehyde and our alkene functionality in our first product. But this problem has two products. So this intermediate is the same as this one, it's just rewritten in red. So when we compare this product to our intermediate, it's really two big differences. One is our C8, our primary radical here has become a methyl group, so a clue there is probably going to do a hydrogen abstraction. And then this acyl radical has ultimately become a carboxylic acid. That carboxylic acid, because we've got a bonus oxygen, is where the water is going to come into play. So the abstraction of the hydrogen occurs from this position. This allows us to reform a pi bond, or to form a pi bond that gives us our CH3 group intact, but then produces this intermediate. You might remember from class 1 that this functional group is a ketene. So two consecutive double bonds, it's like an allene, but one of those double bonds is to oxygen. Looks kind of weird, sort of rare, but it behaves just as you would expect a regular CO double bond to react. It's attacked by nucleophiles such as the oxygen in water, and then as this mechanism shows, nucleophile attacks the carbon, pushes the pi electrons onto the oxygen. We can rewrite this intermediate anion either negative charge on oxygen, but it really behaves more like negative charge on carbon, which can then be protonated, and then ultimately that's going to give us our carboxylic acid. So this last part in red, everything except the first step is our acid base excuse me, or nucleophile electrophile polar type chemistry. Next problem, this single starter material, single enantiomer, is giving us these 6 different products. So again, photochemically, carbonyl is excited. We write it as this type of diradical. Some of our products have OHs, so that would imply some type of hydrogen abstraction. You'll notice 1, 2, 3, 4, 5, 6, again conveniently located in space, easy for that oxygen to abstract it. And when it does so, it produces this diradical. So an important thing to notice here is that at this position, that carbon is going to be sp2, so trigonal planar. Our stereochemistry is lost when the radical is produced at this position. So we've gone single enantiomer to now something that is not chiral. That's important because when these two radicals then recombine to give us ring closure, you see that because of the loss of stereochemistry, we can get these two different stereoisomers. So this intermediate is the same as this one. We can then see the relationship between this intermediate and these two products. What we see is that these are enantiomers differing at the stereochemistry at this position. One is just the start material back, the other is the enantiomer. So this is really the reverse of the first step. So this is just hydrogen abstraction getting back to the start material, but because we've lost our stereochemistry because of this achiral diradical intermediate, when we go back to our starter material, we can get both enantiomers being formed. So this single enantiomer producing this diradical, then producing these two, is really correctly described as a racemization or a self-racemization. We're doing hydrogen abstraction, giving an achiral radical, and then when the hydrogen is returned, you end up with both enantiomers. The last pair of products are in the middle as described in blue. So again, same intermediate. So what we have here is now our radicals are doing a cleavage. So that cleavage is going to break this bond. So breakage of this bond with the electrons moving like that, then get you to your double bond alkene here, reforming or forming a pi bond here gets us to our enol, and we've already discussed the keto-enol tautomerization that ends up at this product ketone. And then for this one, the overall reaction is we have this ketone that's going to the same ketone, but we have this triene being isomerized into this more stable, basically all or more trans diene. So the overall transformation is really just this cis double bond into this trans version. So triene to triene isomerization, producing something that's more stable. So this is an example of a photochemical reaction that is done indirectly, meaning we're using a sensitizer. The N to pi star excitation can only apply to our ketone. So the N is referring to non-bonded pairs of electrons or lone pairs. Ketone has that, triene does not. So this N to pi star is impacting or interacting with the ketone. It's photochemically exciting it. That's what we have donated here. Then that excitation is passed over or transferred to the triene. So you can see now our ketone has lost its excited state, but it's transferred that energy to the triene. We can approximate this triene as some type of diradical species, and the diradical species, because the pi bond no longer exists, is free to rotate. That rotation will give us a more stable conformation, and then when the diradicals recombine to form a pi bond, it produces the more stable trans orientation.